Okay, let's start to talk about Hodge number. Let's still first start with one-dimensional filter vector space. Let's say, suppose T is a filter vector space over K, one-dimensional. Then we define the Hodge number Th of D to be the maximal integer such that the filtration I equals D itself. We know that this is when the index I increase, the inclusion relation becomes smaller and smaller. And in other words, this I is the integer such that field I of D equals D, but field I plus 1 equals 0 because this is one-dimensional. This is a chain of subvector spaces, and so it jumps to dimension 0 at index I. There is another, so we use this one-dimensional, this definition of Hodge number for one-dimensional to define for a finite-dimensional H as follows. So let D be again a filtered vector space over K and with dimension H. And we define Hodge number Th to be the Hodge number of the one-dimensional filtered vector space over K. Wedge HD, where this wedge HD is the top exterior power of the equivalent with quotient filtration from this tensor product. Okay, so using this, we have defined what is this Th for any finite dimensional filter vector space over K. And we're not satisfied with this. We're going to give an alternative definition to show the equivalent. But before that, let's quickly recall some very basic things from the alternating product recall. So this recall part, we're following Long's algebra book. So let's consider the category of modules over a commutative ring. R, recall that R multiple map, multilinear map, let's say. From ER, so this is E product with itself R times, and E is just the R module. Okay. Is said to be alternating if f x1 x to xr is 0 whenever xi equals xj for I different from j. I denote this ideal AR with the submodule of the tensor product TRE. So in other words, this is just E self tensor R times generated by all elements of the following form: x1 tensor x2 tensor xr, where xi equals xj. There's some repetition sum. I different from j. We then define wedge R E equals this tensor product R times quotient by AR. Then we have an R multilinear map. This is by the universal property. No, this is just by construction. This is an R multilinear map. Because this quotient that doesn't change. So this is, yeah, because this is what we have mentioned. We recall that an R multilinear map is said to be alternating if this is 0. And so this is already a R multilinear map if you just map it here. Maps x1, x2, xr to their tensor. This is already R multilinear. And then this is again R multilinear because the quotient doesn't change the R multilinear fact. Moreover, this should be the alternating one. So this is by our construction, wedge RV, and this map is actually co-canonical map. Canonical map, and so later, based on this canonical map, we will show it has a universal property. Right? It is clear this is alternating because we have just quotient those relations, stop it, obstruct it from alternating. Furthermore, so put this as a remark. Second, furthermore, it is universal with respect to R multilinear with respect to R multilinear alternating maps. I.e. Let's describe this. In other words, for any other given R multilinear alternating maps, we claim that there exists a unique, so let's, as you draw diagram. We have a R canonical map for any other such kind map. There exists a unique factorization. such that diagram commutes. Let's have a sketching idea. This F lower star exists because we can first get an induced map just using the universal property of a tensor product for multilinear map. Making the diagram commutes just as E module. Don't care is alternating or not. And so we have this, there's canonical map, and this is in particular multilinear, and then by the universal property of tensor product. But this map is alternating, it implies that this induced map vanishes on those AR, and hence inducing our F lower star. Third remark, the image of an element ER under the canonical map into this wedge. RE is denoted. So this is introducing this notation. X1 wedge dot 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 wedge XR. It is also the image of this X1 tensor, X2 tensor, XR in TR, or say under the map from TR of E to wedge R of E. First remark, in this way, this wedge R becomes a functor from modules to modules. Indeed, let U be arrow from E to F of our modules at given elements X1, X2 to XR in this R module E. Then how do we construct the arrow? We can map this X1, this couple X1, XR to UX1 wedge UXR. This is inside the wedge R of F. And then, because this is multilinear and alternating, So by the universal property, and therefore by the universal property induces a homomorphism wedge R U from wedge R of E to wedge R of F, which means that map factors through the canonical map, right? So I've constructed the map from E to wedge R of F. Here we have the canonical map, and because this U is alternating and multilinear, so it factors through, gives you some U lower star, which we denote by wedge R of U. And one checks easily, so this U associated to wedge R of U is functorial. So the fifth was already the fifth remark, kind of example of this concept. So there are applications so in differential geometry, when this E, R module E, is the tangent space of a point or manifold, or the dual space of the tangent space. Either way, this is our module. It should be vector space even in that situation. When taking the dual, the construction gives rise to differential form. Sixth remark, let wedge of E be the direct sum. So there is no wedge R. Where is the R? So I'm going to write it as graded ring. Wedge R of E bigger or equal than 0. We shall make this wedge E into graded R-algebra and call it the alternating algebra. The alternating algebra, or exterior algebra, so of E, or Grassmann algebra. So it has many different names in literature. We now discuss the general situation. With arbitrary graded rings. So let G be an additive monoid. Let A direct sum of AR, R in G be a graded, G graded R-algebra. G graded R-algebra. Suppose given for each graded ring piece AR, a submodule of it. Let's call it denote small AR, and let's also take direct sum of all those submodules denoted by A, direct sum of AR, R in G. Assume A is an ideal of big A, then this A is called homogeneous ideal. Actually, definition of homogeneous ideal is that if this ideal could be written as direct sum of its homogeneous part would mean there is some grade. Could write that direct sum of those graded pieces. Think an example of polynomial rings. Homogeneous ideal. And we can define a graded structure on a quotient ideal. Indeed, consider the following bilinear map. So from the piece AR, product AS, to the piece AR plus S, which sends this ideal AR, product AS, into so this is a very weak notation. Because this is idea. And similarly sends AR tensor AS into a R plus S. Thus, using representative AR and AS respectively, we can define a bilinear map as follows. From AR quotient ideal AR, product AS quotient. Sorry, so here is small AS, of course. Ideal AS map it to AR plus S quotient ideal AR plus S. because it's factored. So firstly, you have this map. This map factors to this because those quotients are in the ideal, are in the kernel, right? So let me put it like this. You have this, and then this quotient, and you also have AR quotient AR, AS quotient AS, and then you notice that factors here because they're in the kernel, their image under this map. It's always in this quotient, small AR process. And thus this implies a bilinear map. From A, so this is just a piece of it. So take their sum from A quotient A. Product with quotient A and map it to A quotient. So this notation just means this AR. Okay. This is it. Which makes this A quotient A into a graded R-algebra. We apply this to tensor product of ER modules and the modules defined as before. If small xi equals small xj, I doesn't from j, in a product x1 wedge xr, and then for any small y1 to ys in R module E, we see that x1 wedge xr, wedge y1 wedge ys lies in a R plus S, and similarly for the product so I just recall what is AR. I think as before is the AR such that you can see it is the span of all those. Let's recall span of all those x1 tensor xr with xi equals xj for some I different from j. Okay, and then by the discussion here, give it graded R-algebra structure. This still works. So So as we said, this is in AR. This is in AS, so altogether it is in the ideal AR process. And similarly for the product on the left. Hence, direct sum of all these AR is an ideal of this tensor product of all these R vector R modules E. Because we recall that we have defined this Wedge R of E to be TR of E quotient by AR, and we were applying the general discussion for graded algebras coming from graded discussing how to make A quotient A into a graded algebra, knowing that A itself is already a graded R-algebra and small a are submodules on each piece quotient by the, yeah. Here in our case, this is saying that we have this as graded R-algebra, and then R is some module in each graded piece, and altogether is telling you that Wedge RE is a graded R-algebra, and also it's direct sum, right? We hence can define R-algebra structure on this T quotient A, right? This is the product of homogeneous element is given by the formula x1 wedge x2 wedge xr y1 wedge y2 wedge ys it's mapped to wedge of all the elements. This give a ring structure on elements. More precisely, this is giving you the product on the pieces, right? This is tell you we have a map from TR, quotient AR, product TRS, quotient AS to TR plus S, quotient AR plus S. Give it in particular multiply a product on elements and hence a ring structure. We use the symbol wedge also to denote the product in this graded R-algebra. This product is called the alternating product, or exterior algebra, or exterior product. If so, this is a small remark. Let's say sub remark 7.1. For any x in E, Y in E, then x wedge y equals minus y wedge x, because we have, by definition, small ar, this is contained in small a2, and so this is 0. And by the alternating tells you that (7.2) we observe wedge is a functor from the category of modules to the category of graded R-algebra. To each linear map from E to F. We obtain a map from its wedge, from its alternating algebra to this alternating algebra, which maps wedge to wedge. Furthermore, this is a homomorphism of graded R-algebra. So lastly, let's recall there is a very important proposition. I'm not going to go prove this. Actually, this proof is not very difficult. This is sometimes combinatoric argument. Let E be a free R module of dimension n. If R is bigger than n, then we claim this exterior algebra is 0. Because, as you could imagine, if its dimensions are n, then you take R times wedge, then even use basis elements, so some of them will be repetition and gives you 0. Now let small v1, v2, vn be a basis of this R module E over R, free R module. If this, for any R less equal than n, then this algebra is not trivial. And then we can say something more subtle. We claim that this is then again a free R module over R, and actually we can give a precise basis weight and hence got a dimension weight. Elements for the following form, so no repetition. If you changing the order, it's at most changing the sign. So after rearranging the order, let's assume those index is increasing and there is no repetition, and they form a basis of this exterior algebra. Over R. And hence we have a dimension over R for this exterior algebra to be, you just select R vectors from the n basis vectors, so C and R. Okay, I'm going to go prove of this. So after this recall, let's start to do what we really want to do today. This is like claim to give alternating definition of this Hodge number and show it is equivalent to the already given one at the very beginning of this video. So now we want to give alternative description of this Hodge number of D. So for filtration, field I of D, I is integer. We see that there is a jump in the filtration at J's position. If this field J doesn't equal field J plus 1 for a given filtration on this filter vector space D over K, let There are just finitely many jumps. So let G1, G2, GS be the jumps. The finitely many jumps comes from the definition of a filtered vector space. So also in the filtration of the top exterior power, which is also the wedge exterior algebra we just defined. The top exterior power, there must be only one jump because it's one-dimensional R modi p-vector space. And that jump is defined to be the Hodge number of D, right? Notice this characteristic of K is 0. And so this wedge H of D how to say this? I would rather write this quotient by some relation, right? And the subspace filtration coincides with the quotient filtration of the top exterior power. Filtration on the tensor product is given as filtration I tensor H D equals summation filtration on each piece such that the sum of all those indexes equals I. This is the filtration of the tensor product. We are looking for the largest because we have already defined one. Hodge number is defined to be looking at the jump index of that one-dimensional k-vector space, which is the exterior H of D. And now we want to, instead of using this, we want to say the same number, can I find a different expression? That's given the alternative definition and its equivalent, right? I'm just giving a different expression of that. So looking for largest possible choices for this I1, I2, H such that phi line 1 wedge, phi line 2 wedge, phi line H is non-zero. Also, since this product is symmetric in all terms, we can arrange the order of the index such that I1 is less equal than I2, etc. less equal than IH. Hence, of the GS, since the GS is the largest index for a jump, simply because G1 is less than G2, less than G3, less than GS. GS is the last jump, it's the biggest one. And hence we want to put as much. Hence we want to put as much I equals GS as possible, but have to make sure the wedge is not zero, right? Hence, we're going to put what? Put the same number of index as the dimension of feed. Dimension of, let me think, what do we put here? Feed GS. Right. This works because FitJS is the smallest one, and so it's contained in all those. It's -1 and right. FitG1, I would say. You cannot put too many. If you put more than the dimension D, hence denote D the dimension, and we're going to put D of those index to be this greatest possible index to make it non-zero. We're going to put D of it, so we will put IH equals IH -1 equals IH minus D. actually, let me think. This is already d plus 1, so this should be this, right? And similarly, if your dimension of field GS minus 1 is, let's say, suppose it's D1, then you should put, because you already put D here, then you should put D1 minus D, which is the dimension of field GS minus 1 quotient field GS of D. And we give a notation for this. Denote this graded piece of JS minus 1. Good. And then you should put that many of the left ones. So let's say IH minus D plus 2 equals IH D plus 3 equals IHD. I mean, here altogether we have D. Here altogether we should have dimension of JR, JS minus 1. And here we should put plus 1 plus dimension of JR, JS minus 1. Put all of those equals GS minus 1 and etc. Continue this process. So finally, what is the relation we got? This, if you add all those R together, this is now all those JK. For each JK, how many JK are there? It's the graded piece of JK. It's dimension over K. K from 1 to K from 1 to how many J here? 1 to S. So this is also the same as, just you could write as I times dimension of graded piece of D for the integer, because it will be automatically 0. Now I mean, exercise is to give an alternative. Exercise is to give an alternative definition. And start here, you could think of it as a solution. Finally, we have give alternative expression. Why? Because, so, TH of D is defined to be this is a TH of, this is our old definition. It's defined to be TH of wedge of D. dh of wedge of d is defined to be the filtration such that the filtration equals itself. So from the discussion above, such an I would be the index such that field I wedge dh is not zero, which is the largest possible indexes such that the addition of those R equals H. Was I, sorry. And from the above equality of sums, this is actually this largest possible sum is actually the summation of I times dimension of k discrete piece, discrete quotient, and hence this is alternative formula for the Hodge number.